Alfred Nobel was the inventor of dynamite. Nobel's first great invention was intended as a scientific aid to man's control of the forces and forms of nature. It was his dream to make possible such great engineering achievements as Boulder Dam. But if a world gone mad used the instruments which he had forged on the anvils of science for the destruction of man and his property, his disillusionment and bitterness may be shared by all those who had high hopes for the constructive use of his genius in the pursuit of peace. Remorse filled him with the thought of the extent to which explosives had been used in warfare. At his death, he left his entire fortune, reputed to be about $8 million, for a purpose not only Nobel in name, but noble in nature. The Nobel Prizes emphasize reward and celebrate the highest achievements of the spirit. They are a tribute and an aid to men of thought upon whom depends the progress of the world. From the interest on a capital fund of $8 million, a prize of approximately $40,000 is awarded to each of those who have contributed materially to the progress and benefit of mankind each year in 5 distinct fields, namely physics, chemistry, medicine, idealistic literature, and the advancement of peace. The legacy and the award are international. Dr. Irving Langmuir was the first industrial scientist in this nation to receive the coveted Nobel Prize in Chemistry, which the Swedish Academy of Sciences awarded him in 1932. Dr. Langmuir is anything but the prototype of the average man's conception of a great scientist. A mental genius, though he would be the first to deny it, he claims that the theory for some of his best work has come to him while motorboating or while skiing in Switzerland. He also pilots a plane and enjoys the sport immensely. And he is proud to relate to his intimates how he founded the first Boy Scout troop in Schenectady. There is scarcely a person living today who is not benefited by Langmuir's researches and discoveries. His creation of the gas-filled incandescent lamp, which turns night into day, is estimated to save the American people $1 million a night in their light bill. Langmuir has made distinctive contributions to the field of radio with his development of the high-vacuum electronic tube used in radio transmission, again benefiting millions in their homes. Atomic hydrogen welding, developed by Langmuir, has advanced the art and efficiency of great industrial pursuits. We are privileged now to take you to the General Electric Laboratories in Schenectady to see and hear Dr. Langmuir as he works on some of the experiments in surface chemistry for which he was awarded the Nobel Prize, and the further discoveries that he has made since the award. His studies of oil films on water, one layer of molecules thick, about 1/10,000,000th of an inch in thickness, spread before our eyes the infinite building blocks of basic science.
When I went to high school and studied chemistry, I was told that chemical elements, such as iron or copper, were made up of atoms, and that substances like sugar or water were made up of groups of atoms called molecules. But now at that same time, I was told that all this was just a hypothesis or theory, and that you never could really hope to find out whether atoms and molecules really existed. That seemed to me very unsatisfactory. The atoms either existed or they didn't exist, and if they did exist, it seemed to me there ought to be some simple way of finding out about them. Many years later, when I was studying tungsten filament lamps, I found that single layers of atoms on the surfaces of a hot filament were sometimes very important. That naturally made me want to try to find some still simpler ways of studying surfaces and thin films on them, and to see if I couldn't find out something about the shapes and sizes of the molecules that make up these films. It occurred to me that nothing could be more convenient for this purpose than a water surface. You can use a photographic tray, or, still better, is one of these trays that you can get for about 20 cents. But it should have a black surface on the bottom so that you can see what's going on the surface. You can take paraffin and melt it, and mix it with carbon black that you can get at any paint store, and then pour this molten mass in the bottom of the tray and let it solidify on cooling. You also should take the edge of the tray and rub it with paraffin, and then rub it with a cloth or your fingers, so as to make the edge of the tray greasy so that water won't pour over the edge too easily. Then you fill the tray with water. Ordinary water will do, you don't need distilled water. And fill it so that it's right up to the brim, or even tends to almost to run over the edge. Now when you have the tray full like this, so that it's about a 1/16 of an inch above the level of the edges of the tray, you can see easily dust particles on the surface. And a more convenient form of dust that you can is sulfur powder or flowers of sulfur. You can put that in a salt shaker and dust it on the surface in this way. The powdered sulfur on the surface makes it possible to observe motions of the surface. For example, I can blow on the surface and push the sulfur around on it. I can even blow the sulfur all to one end of the tray. But that's only possible if the surface is clean, that is, has not been contaminated. If you haven't washed your hands very recently and you touch your hands to the water in the tray, you'll find that there's a contamination that prevents that free motion of the sulfur. Now I'll illustrate that by putting under my hands a very small amount of olive oil. Here's a little bit of olive oil. I take less than a drop and put that on my hands like this, and I'll rub my hands so as to get this well distributed over my hands. And then, putting a little more sulfur on the surface, I'm going to just touch the water in the center of the tray. And you see, a film of oil, olive oil apparently, spreads out from the surface, contaminating the surface. Now that looks like perfectly clean water, but actually that is a layer of oil. If I do that a couple of times more, the surface becomes saturated. It doesn't easily take up any more oil. And now I see that it's very hard to blow the sulfur. If I do blow it, it immediately comes back to the center again, and after I put on still more, it becomes impossible to blow the sulfur. The surface now is badly contaminated. You can't do anything with it for experiments such as we plan to make. So we have to find a way of cleaning it. And for that purpose, I want to use a barrier. You can use a strip of glass, cut about an inch wide off a pane of glass, and put paraffin on it so that it won't be wet by water. But the best thing that we found is to use a chromium rod, a chromium plated rod like this. You can buy for about 25 cents in many stores. It's a rectangle, a square cross section. And if you cut out the central part of that with a hacksaw, so as to make rods, square rods of this shape, you'll find them extremely useful as barriers. Now you can clean those with a towel and get any grease off, and put them down on the surface of the water like this, and move that to the far end of the tray, pushing all the contamination ahead, and leaving behind a clean surface, as you'll see here by the fact that now I can again blow the sulfur to the end of the tray. There are better ways of showing the motion of the surface of water than to use sulfur powder. For example, what I like to use best is a uniform visible film that you can get by applying the right kind of an oil to the surface. You've seen that when oil drips from an automobile on wet pavement, it gives iridescent colors. Now, you wouldn't like to see those colors on your favorite swimming pool, but for this purpose, they are very useful and quite beautiful. Now, you can't use just any kind of oil for that. For instance, the olive oil that we used a little while ago spread out to give an invisible film. That would be true also of animal oils and vegetable oils like lard or cottonseed oil or anything of that sort. On the other hand, if you take a pure mineral oil such as a liquid petrolatum and you apply that to the surface, you'll see that it stays on the surface as a lens. That is, it doesn't spread out at all. Now, you can't see that perhaps very well that way, but if I hold a card back of it, I think you can see it a little better. Now I can get rid of this drop of oil by a barrier. And I'm now going to put onto the surface a little of an automobile oil that's been used in the engine of an automobile, drained from a crankcase. So it's been highly oxidized. And I'll put a small amount of that on the surface, and it spreads out to form a film that isn't very easily visible. It's a dull gray. I think perhaps by getting the reflection from this card you can just see it. But it isn't the strongly colored film that we see on a wet pavement, for example. Now we can do better than that by taking mixtures of this oil and this oil. That way, this gives a film that's too thin, and this one gives one that's too thick. So by adjusting them in the right proportions, we can get any thickness we like, and as we vary the thickness, we get different colors. So we can choose an oil that is most satisfactory to our purpose. And this is an oil of that kind. I'll place a little of this on the surface. Perhaps you can see it spread out from the surface, and you certainly can see it easily if I use the card to increase the visibility. Now with that, we can render the surface visible more easily than with sulfur. But you see, to do it, you need a lighted surface from which you can get reflection. And the next experiments that I'll show you then are taken with a strongly illuminated card in this direction, and I'll ask you to look over my shoulder at the surface of the water so as to see what's going on on surfaces that are made visible by the use of this indicator oil, as we call it. With the light arranged the way it is now, you can see a reflection of my hand very easily in the water. There are a great many substances you can spread on water that give films that are so thin that you can't see them on ordinary water. But this indicator oil renders them visible. I'll put a little of the indicator oil on the surface here and let that spread out over the surface in this way, and then compress it, hold it in place by a barrier. Now I'm going to take a very small wire, and I'll put onto it a little olive oil. Oh, very little. I dip it into the olive oil, but then I drain it out as I take it out of the bottle, and then I wipe off nearly all of it with my fingers, like that. So there's very little, entirely invisible amount. If now I release the pressure here and touch it to this surface, you see it spreads out to form what looks like a visible film. But really the film is invisible, because if I do the same thing over here on this surface, you don't see anything. Now, there are other substances that spread in that way. A very interesting one is camphor. For instance, here, I'll take a certain amount of that film of oil. I'll hold a little piece of camphor out over the surface here, and you see that before touching the surface, it spreads out to form a film. If I do touch it, it goes a little further, and little fragments of camphor dance over the surface. But a film spreads out from the camphor on the surface rendered visible by this oil film. Now that I can do the same thing, show it in another way. There are toys made, sold in many stores, that are propelled by camphor, little boats. And I can make one very easily here by just cutting it out of cardboard in this way, and making a square end, and then making a little recess at the back, in which I'm going to put a little camphor. You could use a fragment of camphor, but I'm going to put on a little of a camphor solution in alcohol, a strong camphor solution in alcohol, and I'll just apply a little of it at this point here to now my camphor is on this surface. If I drop that on the surface of the water, and you'll see that it goes around in a circle, and if I put on the surface now some indicator oil, you'll see how it travels through this indicator oil, leaving a wake behind it as it travels, showing that the film is being expelled from the rear end. Now, if I compress the film, however, the wake closes up and the motion of the boat stops. You saw before that from the film of olive oil that's spread out over the surface, an extremely small amount of oil will cover a large area. Actually, if you make measurements and weighing a very small amount of oil, you'll find that about 1 milligram, or really about a 50th of a drop of ordinary size, will cover a square meter, which is about 10 square feet. And that corresponds to a thickness of only 1/10,000,000th of an inch. That's the thickness of these films, invisible films, that are made visible by the indicator oil. If you take a teaspoonful of oil, it'll cover about 2 or 3 acres. And I've actually tried that up on Lake George. On a day when there's some wind blowing, moderate wind, you can see that it actually quiets the little ripples over the surface, or about an acre will be quieted by only a teaspoonful of oil. The films of olive oil that I showed you a little while ago were only about 1/10,000,000th of an inch thick. It would take 100,000 layers like that, placed one on top of another, to make a layer as thick as a piece of ordinary paper. Now, what's the meaning of that dimension, 1/10,000,000th of an inch? Various experiments made with just apparatus just like this have proved that those layers are only one molecule thick, so that the 100,000,000th of an inch really measures the size of the molecule. Other experiments made with substances whose composition we know shows that we can even measure the shapes of the molecules and find that some molecules are much longer, some perhaps 5 times as long as they are in diameter. The substances I've just used are things like fats and oils, but there's a very interesting class of substances called the proteins that also spread on the surface of water in this way. For instance, egg albumin, made just the white of an egg, or you can get egg albumin at a drugstore, is one. Pepsin, that is in digestion, is another. Insulin, and then all the classes of the things like toxins and antitoxins that are so important to the doctor and the biologist. They spread on the surface of water in that way. So I'll show you some of them. I have here a solution of egg albumin in water, about a 1% solution, and I'm going to form a film from that. So I'll place on the surface a little of the indicator oil, not too much, and then I'll apply this solution, letting it fall very slowly on the surface. And as it flows out, you see it forms a film that has a jagged edge. Now, if I apply a little more indicator oil in the center of that, it gives a star-like figure, quite different from what I would have had if I'd used a single layer of molecules of olive oil, for example. Now if I compress this film, you see it's very elastic. I can compress these up into a small area, and they still hold their shapes more or less, but they expand again. I can break up these little pieces of film into smaller pieces, and you see you get a great many fragments of this film that act as almost like cakes of ice in a lake. Quite fairly rigid fragments, but yet compressible. Now if I'd had different kinds of proteins, I would had very different results. Gelatin would give circular patterns, and some others, some proteins made from wheat, for instance, give one with a very jagged outline. And in this way, you can detect and study the properties of extremely small amounts of proteins of different kinds, and use it as a method of identifying it. Within the last few years, we found that we can transfer these thin layers of thin films or single layers of molecules from the water surface onto metal or glass plate. And that's done just by applying certain kinds of films, fatty substances, and dipping the plate in and taking it out again and dipping it again. And each time that we go down and come back, we fold on a new layer of molecules. We call these multi-layers. When you get enough, you get colors, just like the colors that you get with the indicator oil. And Dr. Blodgett has found that with the right thicknesses and the right kind of film, you get a surface that gives very low reflection. In fact, you may entirely eliminate the reflection of certain kinds of light. And I'm going to ask Dr. Blodgett to tell you about those recent applications she's made of this work.
Glass usually reflects light, and for this reason it is often difficult to see an object behind the glass. You may have been noticing the reflection from Dr. Langmuir's spectacles as he was talking. But it is possible to treat glass in such a way that it will not reflect light. This is done by coating both sides of the glass with a special type of film. The film must have two features. It must have a thickness which is just 1/4 wavelength of light, which is a thickness of 4 millionths of an inch. This means that it would take 250,000 of these films to make a thickness of 1 inch. The film is made by piling up molecular layers one on top of the other by the process which Dr. Langmuir has been describing. Each layer has a thickness of 1/10 millionth of an inch, so that it takes 40 of these layers piled up on top of each other to make the non-reflecting film. The other feature which the film must have is that it must have a very low density. That is, it must be a substance which is 1/2 solid and 1/2 air. In other words, it is just a skeleton or a framework filled with tiny air spaces. When glass has been coated with a film of this type, and a ray of light is directed at the glass, the light reflected from the upper surface of the film interferes with the light reflected from the undersurface in such a way that the two rays neutralize each other, and no light is reflected. I want to show you some samples of glass which have been coated with a film in such a way as to make them non-reflective. This meter has a glass cover, and one side of the meter, the side nearest the bottle, has been coated with a non-reflecting film, while the other side, the side away from the bottle, is ordinary clean glass. You will see that the clean glass reflects much more light than the coated glass, and as I rotate the mirror, you can see that the reflection is quite troublesome from the clean glass and much less troublesome from the coated glass. Also, the coated glass actually transmits more light than the clean glass. This film was made by building up 40 molecular layers to give a film of the required thickness, and was made of a substance, 1/2 of which was soluble in alcohol, while the other half was not soluble. The film was then soaked in alcohol and the soluble half removed, leaving the necessary framework or skeleton of low density, that is, the substance which is 1/2 solid and 1/2 air. I've put on a pair of spectacles which have one lens of ordinary uncoated glass on this side. The lens on this side has been coated with a non-reflecting film from this edge over nearly to the nose, about this far. You'll see that the reflection is troublesome from the uncoated glass on this side, but it's not at all troublesome from this lens over as far as this line of demarcation. When I turn my head away from the light, both lenses appear the same. The non-reflecting coating on this lens is soft, and if I were to wipe the lens with a handkerchief, I should wipe the film right off. But we are interested in studying these films to study the non-reflecting properties of glass which has been coated in this way, and to study the extent to which the reflection from glass can be eliminated.
The experiments with oil films on water were started for the purpose of finding out something about the forces that hold molecules on surfaces. They soon led to the discovery of the cause of the spreading of oils on surfaces and to accurate methods of measuring the sizes and shapes of molecules. The work with proteins has helped, or will help, I think, the doctor and the biologist in their fight against disease. The experiments with the building up of multiple layers of molecules on surfaces has led to the production of non-reflecting surfaces on glass. This all illustrates the fact that experiments started perhaps just for the fun of it or to satisfy scientific curiosity often lead to unexpected, useful results in fields that could not have been predicted.
The Nobel Prize was awarded to Dr. Langmuir for his significant discoveries in surface chemistry, of oil films on water, and of properties of molecules 1/10,000,000th of an inch thick. As civilization has benefited by his creation of the gas-filled incandescent lamp, his development of the high-vacuum electronic tube, and atomic hydrogen welding, so may we look forward to further benefits from his molecular and protein studies, aiding the doctor, chemist, and biologist, and with his associate, Dr. Blodgett, the practical advancement of invisible glass